This is AP Calculus AB, and in this video I'm going to talk about section 6.5, the trapezoidal rule. And what we're talking about here is something that we refer to as trapezoidal approximation. And trapezoidal approximation is another way that we can approximate the area under a curve. So back in section 6.1, we talked about rectangular approximation. And one of the issues we ran into with rectangular approximation was that when we had a table of values, if we did a left-hand approximation or a right-hand approximation, we would essentially disregard one of the points in our table. And really a midpoint approximation, like we discussed back then, was a very, very bad way of dealing with the table of data, because we could only use a midpoint based on the values that we knew. So that required us to throw out essentially half of our data points when we were doing an approximation. So we're going to do a method today called the trapezoidal rule or trapezoidal approximation that is going to allow us to use all the data points. So we're going to talk about how this works. Okay, so let's take a look at this first diagram that you have here. And what this is a set of data points. And we're going to assume that these data points were collected from some function. So we'll just call that function f of x. And what we're trying to do here is we are trying to find the integral on this entire interval. You can see that our points go from 0 all the way up to 21 on the x-axis. And so what I'm going to do here is I'm going to write an integral that goes from 0 to 21. And I'm trying to integrate the function that would give us those points. But we can't actually solve that integral. So we're going to approximate it. Now, we could definitely do a left-hand or a right-hand approximation. Midpoint would probably be a bad idea here. But those are not going to use all of our data points. So what I'm going to do instead is I'm going to use this trapezoidal method. And the way the trapezoidal method works is instead of drawing a rectangle by using either the left hand or the right hand or the midpoint function value, what I'm going to do is I'm just going to connect these data points with line segments, and I'm going to create trapezoids. So for example, I have a point at 0, x is 0, and I have a point at x is 3. If I connect those 2 points with a straight line, and then I draw in a vertical here, you can see that I've now got a trapezoid. And I'm just going to do this with all my consecutive data points. I'm going to create a bunch of trapezoids that are going to approximate the area that would be underneath this function. So we don't really know what's happening between these data points, but this gives us a good way to at least approximate what the expected integral value would be. Okay, so here are all of my trapezoids, and you can see that I've essentially got 1, 2, 3, 4, 5, 6, 7 trapezoids. Okay, so the number of data points that I have, if we just go through and add these up, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 data points, and we talked about 7 trapezoids. So I'm going to do this the long way to start with. You're not typically going to have to write things out this way, but I want to show you this the long way, because when we do a trapezoidal approximation, this is what is actually happening. So our trapezoids, remember, the area of a trapezoid is 1/2, and I'm just going to write area of a trapezoid here. It's 1/2 of base 1 plus base 2 times the height. Okay, so you guys have known that formula for a while, since middle school, and we're going to use that here. We're just going to find a bunch of trapezoids. So when I look at the first subinterval that goes from 0 to 3, you can see I would have 1/2. My function values, or the heights of those points, or the y values of those points, I would have 5 plus 8, because those are going to be the bases of my trapezoid, because they're the parallel sides. And then the height of that trapezoid would be the length of the subinterval, which is 3. So that's my first trapezoid. Now I'm going to do the same thing with the next one. Now I'm going to start with that second point. It was at 8. The next point was at 7. And then again, I'm going to multiply by 3. Okay, so I'm going to continue, and I'm going to write out all 7 of these. So I'm going to continue on the next set. I've got 7 and 4 as my 2 function values. And I've got a height of 3 again. The next one, my left base would have a function value of 4, and then my right base would have a function value of 5. And I know this is a little bit tedious, but you'll see why this is important to have these all written out here in just a second. So now we're going to start with the 5. The next point after that would be at 8. And again, we have a height of 3. And I've got 2 trapezoids left here. So now I've got 8 and 10. And again, my trapezoid has a height of 3. And the last one here, we've got a function value on the left side of that, which would be base 1 of 10. The second one's at 9. And the height of my trapezoid this time is 3. Okay, so in the end, if I were to add all that up, I would get 147. Okay, so that is a true trapezoidal approximation. Now, if you notice here, we can actually shortcut this a little bit because, first of all, notice there's a 3 in every one of these. So all of our trapezoids have the same height. So this allows me to really make this a little bit more concise. Like when we did rectangular approximation and we had subintervals that were all the same length, meaning the base of each rectangle was the same, we could factor it out. Well, if you notice here, we have a 3 and a 1/2 in every one of these trapezoids. So we could really factor that out. Now, when we factor that out, let's take a look at these values. So this value of 5, this first function value, that only shows up within a single trapezoid. So that's only going to be there once. When I go to the next data point of 8, which we're talking about this point now, you can see that that shows up in the first trapezoid and the second trapezoid. This function value of 7 shows up in the second trapezoid and the third. The function value of 4 shows up here in this third and fourth trapezoid. The function value of 5 shows up in these 2 trapezoids. You can see this 8 shows up in those 2. You can see the 10 shows up in 2 trapezoids. And then the 9 is also only there once. Now, if we were to factor out the 1/2 and the 3, you can see that all of those data points or all of those function values are there twice except for the left endpoint and the right endpoint. So what that allows us to do is when we have equally spaced subintervals like this, or trapezoids that all have the same height, we can factor this out. We can factor out the height of the trapezoid divided by 2 because we had a 1/2 and a 3 in there. And now notice this setup. We have the first term there once, and all the terms in the middle are multiplied by 2 because they showed up in 2 trapezoids. So that's just sort of a factored form of what we just did, working it out with all the trapezoids written independently. Okay, so take a look at the next page here. This is the formula that we typically use. So we call this our trapezoidal rule. The trapezoidal rule, or this formula, can only be used when you have subintervals of equal length. And the reason that's important is because we have to be able to factor this h out of all the trapezoids. If that h is not the same in every trapezoid, then we would just have to go through and do it the long way, evaluate each trapezoid one at a time. But when we have trapezoids that have subintervals of equal length, we can use this shortcut. And the nice thing is, if you notice here, the number of data points that we have, we start at, whatever our first data point is, we go all the way to the last data point. We're considering every single data point within our interval. The height that we find for our subinterval, or the length of the subinterval, or the height of the trapezoid, we just do the length of the interval, b minus a, divided by the number of subintervals, which is n. So that's how we do our trapezoidal approximation. Okay, so like I said, you can only use that formula when we have subintervals of equal length. Okay, so keep that in mind. Most of the time when we see this, we're going to have subintervals of equal length, but it's not always going to be the case. So that's something that you need to check before you use a trapezoidal approximation. So let's take a look at an example here. It says, use the trapezoidal rule to find the integral from 0 to 3 of x squared dx with n is equal to 6. Okay, so first thing, let me state the obvious. There's really no reason to actually use a trapezoidal approximation here because we can solve that integral and we can get the exact solution of 9. But we're going to use this integral to do this approximation so you can get an idea of the accuracy that we get when we do a trapezoidal approximation. Okay, so we've got this function x squared. We're integrating from 0 to 3, and we have n is equal to 6. So the first thing is I want to know what's the height of each one of my trapezoids. Well, the height of the trapezoid is the length of the interval divided by the number of subintervals. The length of my interval is 3. The number of subintervals is 6. So the height of each trapezoid is going to be 1/2. So what I'm going to do here is I'm going to integrate, or I'm going to approximate this integral. The integral from 0 to 3 of x squared dx can be approximated by this. No, we're just going to use what that formula said. Our height divided by 2, because remember there's a 1/2 in that formula for the area of a trapezoid. And now I need to get all of my function values. So I need the endpoints of all of these subintervals. So the first endpoint would be at 0. So that's going to show up in a single trapezoid. And now all those terms that were in the middle, all of those function values that are in the middle show up in 2 trapezoids. So the next one's going to get multiplied by 2. When I'm at the right endpoint of that first subinterval, I'm at x is 1/2. That would give me a function value of 1/4. Okay, and then we can keep going through that process. When we get to the next endpoint, we're at x is equal to 1. When I square that, I get 1. And then I would be at the point x is 3/2. When I square that, I get 9/4. And so on. Now I'm going to be at 2. That's going to give me 4. Now I'm at 2.5. That's going to give me 5/2 squared, which would be 25/4. All the way until I get to the last point, which the last value here, there's only one trapezoid that includes the point when x is equal to 3. So I'm only going to put that one there once. Okay, so just like we saw in the formula up above, we've got the first term there once, and we've got the last term there once. All the other ones are there twice because they show up in 2 trapezoids. So at this point, we can add these up, and we're going to get a value here of 9.125 or 73/8. Okay, that's not a perfect solution, but it's a good rough approximation. Now, the actual value of this integral, we know how to solve this from 0 to 3, x squared dx. We could take the antiderivative, get x cubed over 3, plug the 3 in, we're going to end up with 9. So the actual value is 9. So you can see just with 6 subintervals, we got a pretty accurate representation of the value of that integral. If you think back to when we were doing rectangular approximation, we actually did a similar problem to this. And when we had 6 subintervals, we got answers that were pretty far off from the actual value when we did a left-hand or a right-hand approximation. So now we're getting a pretty close approximation. And actually, what a trapezoidal approximation is the average of the left-hand and the right-hand approximation. So you can think of it as, adding up a bunch of trapezoids, but you can also think of it as the average of the left-hand and the right-hand rectangular approximation. Okay, so let's take a look at these next 2 questions. It says, why is this an overestimate? So notice we got a value that's slightly higher than 9. So to answer that, let's think about what this graph would look like. So I'm thinking of x squared. And when I've got the x squared function, it looks something like that, right? So let's just take 2 points on this curve. And if I drew, I'm trying to create my trapezoid here. If I drew a straight line between there, you can see that my trapezoid actually goes above the curve. And the reason it goes above the curve has to do with the shape of the curve. And the shape of the curve there is what I'm interested in, which is the concavity there. And the concavity in this case is what's giving me the value giving me the shape that's allowing me to have an overestimate. So why is this an overestimate? It's because the graph is concave up. Okay, and then the second part, it says, when could the trapezoidal rule give an underestimate? So obviously it would be when we have the reverse situation. It would be when the graph is concave down. Okay, so fairly simple, but again, the shape of the graph is what determines the overestimate versus the underestimate. If you think back to a rectangular approximation, it depended with the left-hand, right-hand approximation, it depended if we were increasing or decreasing with our function values. Here, we're more interested in concavity to determine an overestimate versus an underestimate. Okay, I have one more example here that I want you to try. And what we're doing here is we're trying to find the average temperature. And we have a table of values. And it says an observer measures the outside temperature every hour from noon until midnight, recording the temperatures in the following table. What was the average temperature for the 12-hour period? Now, when they talk about the average temperature here, we're referring to an average function value. So there's different ways that we can calculate an average, right? One way that we can think about this is to think about like a statistical mean, where we add up the points and we divide by the number of points that we have. What we're trying to do here is we're trying to think about, okay, if we took the temperature at every point between noon and midnight, and we looked at all of those points, which is impossible, obviously, because we have an infinite number of points. But if we averaged out all of those points, what would the average temperature be? So rather than just doing a statistical mean, we're really here looking for an average function value. So that's what I want you to do, is try to do this with an average function value and set this up in terms of the integral. The integral is going to be evaluated with a trapezoidal approximation. So you should remember average function value setup, and then use for the integral, use a trapezoidal approximation. So you can pause the video. When you come back, I'll show you the solution. Okay, so here's my worked out solution, and let me explain what I have here. So remember when we do the average function value, we do 1 over b minus a times the integral from a to b of our function, right? So 1 over b minus a, we have a 12-hour time period. That's my 1 over b minus a. Now, the rest of this is replacing my integral. So my integral with the trapezoidal approximation, first thing I want to do is find the length of each subinterval, which is obviously 1 hour here. So I have h divided by 2, 1 over 2. And then I have the first term there once, the last term there once, all the terms in the middle are there twice. I didn't write out every single term because there were a lot of terms here, but that's the general setup that we would use. And once we have all of that, then we can just evaluate that on the calculator, and we get an average temperature of about 65.167. Okay, so remember, that's doing an average function value as opposed to doing a statistical mean or a statistical average like you might have thought to do. Okay, so as far as the assignment goes, what we have is an assignment in Math Excel. Most of these are fairly straightforward. One thing that I do want you to make sure you're considering as you work through the problems, especially when you have data sets, always make sure that the length of the subinterval is the same every single time from one point to the next if you're going to use the formula. The formula only applies when the length of the subinterval is consistent all the way through your data. Okay, so the other thing that I want you to think about is when you're working these problems out, you might be tempted to just plug everything into the calculator and not write any work down. Try to get in the habit of writing down your work in the way that I showed it here, right? So making it really clear what's going on with the process. And we talked about this with rectangular approximation. So when I ask you to show work on a quiz or a test or anything like that, I want to be able to see what your process was. And I want you to get in the habit of this, not just for me, but also if you're going to take the AP test at the end of the year, this would be the work that you would be expected to show. So make sure you're practicing that as you do your homework as well.